All right, so today we're talking about assignment 4, which is using a genetic algorithm to try and solve a Sudoku puzzle. I'm sure most of you have played and mastered Sudoku by now, but I'm just going to go over the rules of Sudoku for anyone who hasn't played it before. It's quite a simple game, and it's a puzzle game, and it's a single agent game. So you're not playing against anybody. It's kind of like a crossword with numbers, if you want to look at it that way. So the standard way that Sudoku is played is that you are given a partially filled out board, and these numbers here that have been given to you, like for example on Sudoku.com, which I'm using here, they have given you these numbers, and those numbers cannot change whatsoever. So those are fixed and you cannot edit them. And your goal is to fill out the rest of the board using the rules of the game. And if you can follow all the rules and fill up the whole board, you've won the game. So the rules of Sudoku are pretty easy. The grid, as you can see here, is a 9x9 grid. So it's a two-dimensional grid. We'll be representing this as a 1D array, but you can, I'll have .get x, y, so you can get things from rows and columns. And the rules are for every row and for every column and for every 3x3 square that are marked here, you have to use all of the numbers 1 through 9 exactly once. And so once you've filled it out, all of the numbers 1 through 9 should be on the board 9 times, but only once in each row, each column, and each square. And that's it. That's the whole game of Sudoku. There are no other rules. The way that they present the game here is slightly different than the way we'll be playing it. So here, the standard way that Sudoku is presented is that it gives you a board that is partially filled out, and then you have to fill out the rest of the numbers so that you can solve the puzzle with respect to the numbers that are already there. But for our assignment, we'll just be starting with a random board of numbers, and you have to use the genetic algorithm to turn those into a solved board. So let's just quickly look through the problem of Sudoku. So for example here, this is an easy puzzle. They go all the way up to like master extreme. And essentially, the way that the difficulty works in these games is that the initial placement of the numbers is either going to be easier or harder to find the remaining numbers based on the number of like logical steps you would have to follow in order to assign those numbers. So I am by no means an expert or master on Sudoku, but let's just have a quick look. So here, for example, you can click around here and it'll show you things like where all the 8s are, where all the 2s are. But let's just have a look at this 3x3 square right here, because it's almost already filled out. And so typically what you do to try and solve a Sudoku board is you'd say, okay, this 3x3 square here, it has a 1, 2, 3, 4. It doesn't have a 5. It has a 6. It doesn't have a 7. It has an 8, but it doesn't have a 9, right? So I would need to somehow put a 5 and a 7 and a 9 in here without breaking any of the rules. So what you would do is you'd say, okay, well, of 5, 7, and 9, let's see, can I put any of those in this square up in the top right of this square? Yes? No, I'm about to say that. Oh, yeah. Thank you, though. Yeah. So thank you for pointing it out. But what I was about to say is that we have to put one of a 5, 7, or 9 here. But putting a 7 here would break the rule that there can't be 2 7s in this row. And putting a 9 here would also break the rules of putting 2 9s in that row. So you would put a 5 there. And then maybe you would look at this one. And you say, okay, there's a 7 or a 9 that has to go in this space, and there is already a 9 here, and so this would have to be the 7, and this would have to be the 9. And so this gives a nice little animation, and what you would do is maybe now you'd say, oh, look here, there's a row that only has one piece missing. And of course, if there's only one piece missing, we can trivially find that. So 1, 2, 3, 4, 5, 6, 7, well, this must be the 8 then. And so you would continue on like this until you've completed the whole board. And because this is an easy puzzle, we only needed like one logical step. and we were always able to eliminate all the wrong answers. But when you get up into like more extreme things, typically there are fewer things on the board, and you'll have to do things like, okay, this square could be like a 3, 4, or a 5, and this could be a 3 or a 5. So now I know it's either a 3 or a 4, and like you'd have to take like it gets pretty complex in some of these larger or more complex Sudoku puzzles. But anyway, those are the rules of Sudoku, and we'll be using the rules, but not the like initial placement of the things on the board. So let's, as we always do, have a look at the assignment. So here is the user interface for the assignment. Let me close this and make this a little bit bigger for you. So there are some controls down here in the bottom left. I'll get to those, but I'm gonna just like zoom in past those so I can make the actual UI as big as possible. So here I am showing the solution code, and what this is going to show is over on the left-hand side, we have a Sudoku board. Over on the right-hand side, we have a graph. And yes, I'll get to what all of these mean. But the Sudoku board over here is going to start as a randomized board of numbers. And yes, all of the numbers can appear multiple times. So if we got super, super unlucky, it could be, for example, all 5s or something like that. It is truly random. I'm just choosing, for every cell, I'm iterating over it and picking a random number from 1 to 9, and then placing in this Sudoku board. Down here, we can also change the size of the Sudoku board. Okay, so that's there. That's pretty easy to change, but let's leave it on 3 by 3 for now. You see here that there are a bunch of different colors appearing for the numbers on the Sudoku board. And what I've done here, just as a debugging help sort of thing, is I have colored the squares darker shade of red, as there are more conflicts with that particular square. What do I mean by a conflict? Well, for example, up here, I have this 1. So there are 4 different colors for this 3 by 3 board. One would be there are no conflicts, 1 conflict, 2 conflict, or 3 conflict. And the conflicts essentially just means how many of the Sudoku rules is this particular piece breaking, right? So up here, I think this is the lightest shade of red for this 1. And so that's because it's breaking 1 rule. And that 1 rule is that there happens to be another 1 in this column. But there are no 1s in this square other than this one, and there are no other 1s in this row. So if I refresh this real quick, you can see that there are some things which are very dark. And so, for example, this 2 has a 2 in this column as well as a 2 in this square. And if it also had a 2 in the row, it would be the darkest shade of red. So basically I did this so you can just visually get a sense for, okay, the lighter the board, the more solved it is, right? Now, we know as Sudoku players that even if a Sudoku board is all white except for like 2 places, it may or may not be actually closer to being solved, right? Because one of the hard things about Sudoku is that, let's say I got down to a board with just 1 red square. Well, if I change that to another number, maybe there is no possible number that goes there that solves the board because of other conflicts that would happen if I actually change that number. So I intentionally chose Sudoku as one of these non-convex problems, meaning that you can't be guaranteed to go to a global maximum. You're going to local minimums or maximums. So over on the right, what you're seeing is a graph. Oh, and the board that you're seeing is that it takes the population and it finds the maximum fitness of the population and then plots that board. So this board is always the best one of the current population, right? So down here, let me show this setting real quick, is that I've got, oh, what's going on? Oh, I just need to move the mouse. Okay. So here are the settings for the Sudoku board. Now I'm going to zoom in now. I'm going to play with the settings later, but I'll just show you what they are for now. I've got a fitness function, and right now there are 5 different fitness functions that I have here, and I'll show you what those are in a second. I've got a population size. So this population size is how many Sudoku boards are there in the population, right? So right now I've set that to 200. The reason I've set it to 200 is because it's like a decent size for the speed that I expect this to be running at. If you pump this up to 1,000, maybe like your program will run a little bit slow. But just to let you know, there is a balance that you have to achieve between population size and the number of generations. Every single operation that we do when it comes to genetic algorithms is applied to the population, right? Now, yes, of course, some things are like applied to individual genes, but for example, if I want to select the parents, I'm going to have to iterate over all the things in order to select those parents. So we can pretty much expect that on average, if I have a population size of 200, each generation is going to be about half the speed as if I was as if I had a population size of 100. So it's pretty much a linear scaling. Like if I bump that up to 1,000, it'll be 5 times slower per generation. Okay, so there is this really strange relationship between how long it takes you to compute all the functions for a particular population and how many generations you actually want to run for. Because if it's taking me 5 times as long to run 1,000 versus 200 population size, well then I will only complete 1/5 of the generations. And as far as I know, it is impossible to tell which is better, right? So you can't just run some function and figure out some mathematics that says running 5 times as many generations is better than the same but 5 times the population size. It's just you have to test it, right? So if you ever do, make your own GA or something, let's say you have 1 hour to come up with a solution, it is unknown whether or not you could bump up the population size and get a better answer in that 1 hour. Because if you put the population size back down, you'd have more generations. So there's always this slider between population size and number of generations per second. So that's just a thing that has to happen. The next thing here is the number of individuals, the percentage of individuals that get mutated. So what this means for our assignment, the base level of mutation is to just take a Sudoku board, choose a random place on the board, and flip that number to another legal random number. That's what I'm going to ask you to do. If you want to get into the weeds and really optimize your Sudoku, I am allowing you to come up with more complex mutation operations, but that is the base level operation that I want you to do for the assignment. So this would basically say that 1 in 4 children get mutated after they're generated. That's about it. Percent random genes inserted. What this means, this colon here is just because it ran a bit. It's supposed to be there, but I'm not very good at CSS, obviously. So percent random genes inserted. This means that, 5% of 200, what's that, 10, right? So every population, I will generate 10 random Sudoku boards and put them into the next population. So that's what that is. Elite gene survival. What this means is that, again, it's 5%. So 5% of 200, every generation, the very first thing I'm going to do is take the top 5% or 10 Sudoku boards, the top 10 fitness Sudoku boards from the previous generation, and just copy them into the next generation. So if this value is greater than 0, it means our maximum fitness can never go down, because the best thing that we had from the previous generation is automatically being put into the next generation. And if your computer can handle it, this slider just says how many generations am I doing per update of the web browser. Okay, so this is running at 60 frames per second. So let me zoom back out. Oops, I gotta do this. So here, if you look, this is running at 60 frames per second. So this X graph is counting the generations. And then what this graph is saying is the blue line is the maximum fitness of any individual in the population. This purple line is the average fitness of all of the individuals in the population. And the green line is the minimum fitness of all the individuals in the population. So this graph is essentially saying, how much is my solution improving over time, right? And you can see the standard genetic algorithm thing of super quick optimization up until a point where it kind of gets stuck and then it's going a bit slower, right? So yes, if you leave this running long enough, it will continue improving, but we'll get back to that. What I wanted to explain is that this x-axis down here is essentially growing at 60 per second, right? Because this is running 60 times per second. But if I refresh this and I come down here and I bump this up a little bit to 17, now it's 17 times 60 per second, right? Now that's not guaranteed because your computer might not be able to do 1,000 generations per second or whatever you set this to, but that option is there if you want it, to come down here and bump up the generations, right? What will happen is if you put this up really far, then you'll see this graph starts to slow down, right? So every time it updates, if you see it start to slow down in its updates, it pretty much means that you've reached the maximum number of generations per second that your computer can handle. So if I continue to bump this up any more, it won't actually make things faster, right? So if you see it start to slow down from like instantaneous, then you're pretty much at the limit there. This laptop is pretty fast, so don't be disappointed if you don't hit the same speed or whatever. Oh, but look at this. When I bumped up the numbers, I've got a pretty close to solved board, right? So if your genetic algorithm is eventually getting to something like this, that's great. You've got full marks, right? Oh, look at this. I don't expect you to get a solved Sudoku, and now I'm kind of wanting to not do the lecture and see if this gets solved, right? But I'm gonna have to refresh this a bunch more. I'm sure it won't, but maybe it will. I think I've solved it like once ever, but my fitness function is terrible, my mutations are terrible, so it's unlikely that I actually get to a solved board here. Okay, so let's, it pains me to hit the refresh button there. Let's look at the other fitness functions. And the other fitness functions are really going to be there for you to be able to test whether or not your genetic algorithm is working as expected. So down here, I've got another fitness function called SumValues. What this is going to do is just try and maximize the sum of all the numbers on the board. This one is match row, then match column. And what this will do is it will try to set the number to the value of the row or the column. So, and the checkerboard pattern, I'll show you that in a sec. So here we go. I'm going to choose SumValues, and you can see that the same genetic algorithm that was trying to solve a Sudoku board is now essentially trying to set everything to 9, right? Because it's just taking that as the fitness function. And what it tries to do is maximize this fitness function. And there we go. I think it's at the maximum. So whatever 81 times 9 is, that is the fitness function that we have here. Let's look at the other ones. Match row. So this will want to put the index of the row in that row. And so the fitness function is literally just counting up however many things match it. And then so this one, 81, would be the maximum fitness, right? Because it's the number of things that have matched. Next would be match column. And so this is the same thing, but you're just matching the column. And the cool thing about this problem is that these are convex problems, meaning that you can always improve your solution without having to go backwards, right? You don't have any of these local minima or local maxima, because I can always take, if I'm looking at SumValues, I can always take a 5 and make it higher, right? And I never have to go backwards. So these are easy problems for this GA to solve. And the last one here, I just said, okay, I'm gonna make a checkerboard pattern out of 1s and 9s, right? So you can kind of see like the power of the GA here, that it is, all you need to do is define the fitness function and it can optimize for that, right? So now, again, these are kind of contrived problems because here you've got a situation where, so for all of these problems, Sudoku, SumValues, all of these, like if you sat down as a human, you would be able to solve this problem very easily. Like you could instantly say, put 1s in the first column, put 2s in the second column, right? So I've made these sort of trivial problems. But if there was some other problem that was non-trivial, like make the sum of the squares of all the values equal to 3,201, it would also be able to solve that problem, right? It's just the fitness function that matters. So if the fitness function is properly constructed and gets you closer to your goal, then a GA is able to effectively, it's not doing exhaustive search, but it is able to search through a large part of the search space. Okay, now let's go back and look at all the different options that we have here. So the options, population size, you know what this does, but changing the population size will not change the graph whatsoever. The only way it would change the graph is that ideally, as you have more of a population size, your progress per iteration is going up, right? You can think about it. If I have 1,000 things that I'm checking every time versus 100, ideally that would mean that I have more good genes that are reproducing, etc., and going up like that. The next few sliders will have quite dramatic effects on the graph. So what I'm going to do here is, remember, this is the maximum, this is the average, this is the min. So I'm going to go down, let me just zoom out a bit more, and I'm going to say, okay, let's increase the number of individuals that have been mutated, right? So again, this one, like population size, is not going to have a direct effect on the graph, but what we have seen here is that, oh, it actually does have a direct effect on the graph, but not a great one, is that as I'm mutating more and more individuals, well, that's kind of changing them all a bit randomly. And if I change things randomly, some of them will be good changes, but most of them will be bad changes. And so what's happening here is you can see, because randomness is like, it's required by GA in order to improve, but too much of it is going to be bad to the average. Because on average, we're making things get a little bit worse. So you can see here, if I change the number of individuals mutated, the average goes down. But ironically, as you change the number of things mutated, depending on the problem, your solution maximum could be rising faster because you're introducing more randomness into the gene pool. So it's like, you start to see how all these different parameters interplay, and it's kind of difficult to understand. Now, hand up if you know what should happen if I increase the number of random, completely random genes that I insert. What should happen to the graph? So let's say now I'm putting 10 random things into each population. What would happen if I put 50 random things into each population? Well, if I put more randomness, what should happen? Yep. The average would be lower. Let's test it. Oh boy, yeah. Because, is a random Sudoku board even close to being solved? No. So the fitness of a random Sudoku board is going to be pretty low, right? And if I put more low things in, the average goes down. That's it. Ironically, again, by putting more randomness into my population, I may have new solutions that, when combined with other things, get me better results faster. But if I have too much randomness, then I'm no longer keeping around enough good solutions to breed with each other. So this is another slider. How many random genes do we want in here? Okay, let's reduce again. Now the last one is the number of elite genes that survive. So remember, this 5 here means that the top 10 from every population go on to the next generation. So this will not have a direct effect. Oh, sorry, it does have a direct, I keep messing that up. This direct effect is that if I keep a bunch of really good ones around, then the average fitness goes up, right? Because I'm keeping more good ones, so the average goes up. However, the unintuitive thing that happens is if I put this to 0, watch what happens. That means that none of the best ones are guaranteed to go forward. Right? You're like, why is the maximum going down? Like, why? Okay, the maximum is still higher than the average, but okay, and it's starting to grow maybe like a little bit, but it's definitely like hitting this plateau. Why did keeping some of the best ones around have such a dramatic effect on this graph? Well, here's one of the reasons. That will not always be the case, but look at this. this graph is a little bit deceptive. Let me make it bigger. Why is this graph deceptive? You're all scientists. You should know why this graph is deceptive. If Fox News put this up there, what would you say about it? Yep.
Scales different than the y-axis scale.
Why is it bad? What does it not do that we should be doing? No, okay. It doesn't start at 0, right? So this minimum looks like it's 5 or 6 times less than this. But this is actually around 145. This is only 200 and something. So the minimum, it just so happens that in Sudoku, if you generate a randomized board, it has approximately half the fitness of a solved board. So think to yourself, do you really want a random board to have half the chance of being selected as a parent as the best thing possible? Probably not, right? So right now, this is just doing vanilla linear roulette wheel selection. So the thing that I worked so hard to get, that those like really high valued Sudoku boards, they only have a slightly higher chance of a really terrible Sudoku board of being chosen. So there are some things that you can do, which I hope that you do in your assignment. For example, one of the easiest possible things you could do would be to change the linear nature of that relationship, right? So you could take 150. So let's say this was 10 and this was 20, for example, okay, to make the numbers a bit easier. 10 is half of 20. So by itself, it would have half the chance of being selected. But let's say I take both numbers and I square them. 10 squared is 100. 20 squared is 400. So now the highest thing would have a 4 times higher chance of being selected, right? So sometimes what you would want to do is to introduce some non-linearity to the fitness function such that the best things in your population are way, way higher chance of being selected than the worst things in your population. Certainly not just half. So what's happening is, if we aren't guaranteed to bring the highest thing over, well, a bunch of our random ones are just breeding all the time, right? And it's very unlikely that our top ones keep breeding over time. Now, depending on the domain, this happens to be true for Sudoku, but let's try another one. Let's try one of these convex functions, okay? So this one doesn't have the same dramatic effect as the Sudoku one, okay? So this is a domain-specific effect that we are noticing, but that you should be aware of. In order to get really good at solving some domains, those fitnesses have to be like super linear chances of being selected based on your fitness function. Okay, so that's just something that I wanted you to notice, and it is very likely that on the final exam, I will be asking questions about what happens to a fitness over time graph when these parameters are being moved around, okay? So just keep that in mind. All right, any questions about the UI before I move on to the code, or if anything is not cool so far? All right, great, everyone's following along. Let's move over to the code. Of course, you've got the marking files. I'll get to that at the end. So you're all familiar with how I do this now. This highcharts.js, that's the library that does the graphing. I did not make that. I just pass in values to it and it updates into real time. So if you ever want a real-time graph on your website for some reason, that is a library that I've been using and really liked over the years. So the first thing we'll look at is this Sudoku class. And so the Sudoku class is kind of like the environment class from previous assignments. And what this does is it just stores and takes care of the logic of the Sudoku board, okay? So in the constructor, this takes in a size. And the size, for example, is going to be 9, right? So a 9 by 9 Sudoku board. So let's look at what's here. So it sets this dot size, so you keep track of the size. this dot square size equals the square root of the size, and that is the size. So if you pass in a 9 by 9 board, at some point you're going to be wanting to check 3 by 3 areas, and so I just compute that once, so we don't have to keep computing the square root. The board is actually going to be stored as a 1D array, and then I'll have functions to be able to get things in 2 dimensions. And by default, the constructor just says fill that whole thing with zeros. So the default constructor just fills the Sudoku board with zeros. Next, I have a getIndex function. And so what this does, it takes in a row and a column. So keep in mind that row column is the opposite of x, y, right? Rows are actually y, columns are actually x. Okay, so when you're calling if you need to call getIndex for whatever reason, or set or get, just realize that you are doing rows and columns and not x's and y's. Okay, so that is a little bit different than in previous assignments. So what this does is it takes in a row and a column and gets us the index of the 1D array that's associated with. That's all. Next, I have a function called randomize. And what this does is it just says for each index of the board, give it a random value between 1 and the size. That's it. So I can call randomize on it. This sets a value based on a given row and column, and it just calls this.getIndex to know where to store that. This is the function that you'll probably be using the most. So you're going to have to modify the Sudoku fitness function, and this is what you can use to get row and column values from the boards. And this is a sample function that I have included in order to do the user interface stuff. So this will take a row and a column and get the number of conflicts. And the number of conflicts is basically, are there any things in the same row with the same value? Are there any things in the same column with the same value? And are there any things in the same 3 by 3 area with the same value? Okay, so that's what that is. That's that function. And you can use that if you want as sample code for your evaluation function later if you think that's interesting. But I've already included a Sudoku fitness function that you can use as a sample as well. So that's what that function does. And then this function down here called setArray is just going to set the value of this Sudoku board equal to an input array. So this is what the UI does in order to draw the Sudoku board. It takes your gene from your genetic algorithm, and it just calls setArray on the Sudoku board, and then it displays it. So you probably will not have to use this, but feel free to use it if you understand it and you want to use it for some reason. Okay, so that is the Sudoku class. It's pretty easy. It just sort of defines the environment that we're working in. Next, okay, so I got the GUI. We don't need to look at that. I have GASettings. So this is where all of those settings that the user interface modifies are stored, right? So we can see here that we have the things that we've looked at so far. So we have the population size, which is initially 200, the mutation rate, which is set to 0.25, random ratio and elitism ratio are both set to 0.05. So that just means 5%. So we know what those are. Up here, however, we have a fitness function. So the settings stores the current fitness function. And if you weren't aware, you can store a function as a variable in JavaScript. And so down here, which I'm going to get to in a second, I've got all of these fitness functions. And then what the user interface does is based on what you've selected in the fitness function, it will set the fitness function in the GA settings. So later on, when you are working with your GA, you have access to this config, and you can grab all of these values. And one of the things you're going to be doing is calling config.fitnessFunction. And no matter what that fitness function is, your algorithm is going to be using that. So this is just an easy way for your algorithm to work with any fitness function by storing that there. Here for Sudoku, the Sudoku size, which could be 9, for example, would indicate a 9 by 9 board. So the individual size, meaning a genetic individual in our population, is going to have size 81. So that's why that is there. So when you create a new individual, maybe you're using this, and so you need that value. The last thing here, which is not super confusing, but I do have to explain it. So this is called individual values. And what this does is it's going to be an array of the legal values that we can have for a gene in this problem. And so what this will be is just an array. If Sudoku size is equal to 9, this will be an array containing 1 through 9. So if you ever want to get a random legal gene value, you can get it using this. You don't have to know, okay, what is the size of the Sudoku board? I need to do some math based on that. This will just hold those values. Okay, so that is the settings. And to make life even easier for you, I've actually included a function called getRandomGeneValue. So when you're doing your mutation, if you've selected an individual for mutation, and then you've selected an index, you can just say this index of the gene is equal to settings.getRandomGeneValue. So I've taken out a bit of that annoying minutia of programming for you. And all this does is it calculates a random index of that array and returns that value. So that's it, pretty simple, that's all the settings. Now here are the fitness functions. So SumFitness literally just sums up the values in an array. CheckerFitness just uses I plus j mod 2. That's a cool way of doing a checkerboard pattern. So if you don't know, if you take the row and the column and you see if it's even or odd, that will tell you whether or not it should be black or white in the checkerboard pattern. Match row fitness just checks to see if it's the correct row, and this one checks to see if it's the correct column. So those fitnesses are just there for you to test your algorithm, or you can use those as template code or whatever if you want. Just realize that those will be stored inside this .fitness function, which is part of the GA settings, which is all done by the user interface. So those are the settings. And if you were doing an actual, actual genetic algorithm, this is an actual GA, but if you were using it for research or trying to solve some problem in the real world, what you might have is some other algorithm that says, run my GA with all of these different settings, right? So you might create 100 different possible settings and then run your GA and see which one produces the best results. And there are actually algorithms that are specifically out there to vary parameters for algorithms like GAs so that you can optimize those parameters. But right now, these are kind of intuitive and nice, and we're just going to leave them like that for now. So if you run everything with those settings, it's fine. Just be aware that any changes you make to these settings in the settings file will not be submitted to me, because you're only submitting the one file like always. Okay, over here, the next thing is, I won't be clicking on solution, but the GA student. As always, we have this function. All right, so the first thing I'm going to do is scroll to the bottom here and look at the Sudoku fitness function. So let's zoom in. And one of the things that you have to do is modify this fitness function to be a little bit better. I'm not expecting you to get the best fitness function in the world. I just want you to take this and make it a little bit better, because my way of counting essentially the reverse of conflicts. So yeah, let me talk about that a little bit too. So the fitness function over here that I have is sort of the opposite of conflicts. So what I'm doing is I'm saying, okay, for example, this 4, so I'm starting a sum at 0, and then for this 4, I'm saying, okay, it's the only 4 in this column, in this row, plus 1 to the fitness. It's the only 4 in the column, plus 1 to the fitness. It's the only 4 in the square, plus 1 to the fitness. So each square on the board is contributing either 0, 1, 2, or 3 to the fitness. So the maximum possible fitness that you can reach using my default fitness function is 81 times 3, which is 243. Does that make sense? Yeah, so that's 243. So a solved Sudoku board up here would be 243. I am expecting you to change that to something possibly wildly different. Now, I know before I said, hey, take those values and square them. If all you do is take my function and square it, you're not getting full marks for that section, okay? I want you to try and come up with something a little bit more clever, and as long as it's more clever, that's all I really care about. Okay, so here's the fitness function, and this is just the code that does what I just said. It's pretty simple. I want you to modify that. And I have included it inside the GAStudent.js file so that your modifications to that function actually do get submitted with the assignment. All right, so that's one of the things that you have to do. But let's read the comments. See if you can modify this function so that the GA gets closer to solving the Sudoku than the version listed here. Note, due to the way ReouletteWheelSelection works, this function must return a fitness for a higher fitness for a better solution, and you cannot return negative fitnesses. So because we are implementing ReouletteWheelSelection, and if you remember the last class when we had that algorithm, if you put negative numbers into that algorithm, it breaks the algorithm. So make sure that all of your fitnesses are between 0 and some larger positive number. And I highly recommend using integers, but you don't necessarily have to. So that's one thing you have to do, is rewrite that to be more clever. All right, now I'm going to have to zoom out just a little bit. Let's go to the top. So this function, the GAEvolve function, is the function that implements this from the slides. So inside this pseudocode for evolutionary algorithms, you've got an initialize population with random individuals. That is done for you inside the UI. So you don't have to worry about that. I am initializing the population with random individuals. Repeat until termination condition. That loop is done for you inside the UI. Okay? So the GAEvolve function does all of these steps. It does one iteration of this main loop that's happening. The termination condition for our assignment does not exist. But what I'm going to tell the TA is something like, run everyone's code and see who comes closest to solving it within some number of iterations. And there'll be a little award for that. Okay? It's not marks based, but I do want to, it's nice to see when people put some effort into it. So these things right here are the things that are going to be done inside this function. So before we get into the function, just have a quick note. Up until now, I've been saying that an individual in our population is just an array of integers. That's pretty much true, but there's a little twist, is that I'm also storing the fitness in there. So rather than just have an individual be an array, it's going to be a JavaScript object containing two values. One variable called gene, which is that array of those values representing the Sudoku board. And the second variable is called fitness, and that is going to be a number, which is the fitness that you are going to calculate for this thing. So because we're going to have to do something like sort the array based on fitness or sort the population based on fitness, that would be super annoying if, for example, you had an array of genes over here, an array of fitnesses over here. Like you'd want them all to be sort of in one object. So an array of objects rather than multiple arrays of different values. So population.gene is a 1D array representation of the individual. That's the genotype. And the population I.fitness is the fitness of the individual. Okay, let's go through this. Very first thing is that as part of 6980, what I'm going to get you to do is go out and research, believe it or not, some theoretical improvement that we have not talked about with a genetic algorithm and implement it here. So you're going to have some way of turning on and off that improvement, and that way is by using this Boolean variable. Okay? So whatever improvement you go out and find, like there are lots of them out there, there are so many papers and websites and stuff that talk about GAs, you're going to do that if that's true and not do that if that's false. Okay? So hopefully that is intuitive enough. So you're going to wrap that behavior around this Boolean. Okay, now the actual algorithm. I've put a bunch of comments in here, so hopefully you don't have to really exit this file much. First, set up a new array which will hold the next population. And so that's it. You're going to set up new next population as an array of those JavaScript objects of individuals, then you are somehow going to populate that array, and then this function will return that array once it has all been done. Okay? So the UI is going to call this function, look at the population that you return, which is the next population, and then it will look for the highest valued individual, and it will draw that on the screen, and then it will draw the stats based on your population. Okay, so I realize that there could possibly be a more clever implementation of this population than an array, but I am enforcing an array for this assignment because it's super easy, and that's what the UI expects, so I don't want to break it. Next, what you're going to do is sort the population descending based on fitness. So the first element of the array is going to be the highest valued individual. Okay? And the reason we're doing that is because the next step, you have to find the top n things. So that's a lot easier if it's sorted, right? Rather than going through and say, okay, what's the next maximum thing, etc. So the next thing we do is take the top n elite meaning the top fitness individuals, to the next population. The percentage of elite genes to carry over is stored in settings.elitism ratio. So if we see up here, this function takes in population, that is the array of individuals from the previous population, and it takes in a settings object. So settings.elitism ratio by default is going to be 0.05. So what you are going to do is you're going to set up a loop. You're just going to, please don't, try not to use too many fancy JavaScript iterators that ChatGPT tells you to. Just use for loops for this assignment. It'll do your brain very well to not use like if sum dot from array dot map reduce. Like just iterate through these things, trust me. So you get a population in. Say that's 500 length. So you can say population.length, right? If you want to get the length of the previous population. If you want to know how many things from the previous population that you have to put in, you have to take that population.length, multiply it by settings.elitism ratio, and that's the number of things. That's it. So you'll set up that loop. I'm not going to do that for you. You got to be able to, you got to do something on this assignment. All right, so that's it. You take the top n things from the previous population and put them into the next population. Okay. The next thing, add the required number of random individuals to the next population. The percentage of random genes to carry over is settings.random ratio. You can get a random gene value by calling settings.getRandomGeneValue. Make sure that you add the following object to the array whenever adding an individual. So this is essentially the code that you'll be using. So let me just, oh, this is too smart. You're just going to take this line of code here, which is nextPopulation.push, this right here. You're going to be creating a JavaScript object with a gene variable named, and the value of that is just going to be whatever gene variable you come up with. So you're going to say, okay, for some number of random things, create a new randomized gene, call it gene variable, and then you can just use this line of code that says nextPopulation.push this, and then you're saying, how do I calculate the fitness function? Well, it's just in the settings. So you, in one line of code, you evaluate the gene and you put it into the fitness of that object, right? So hopefully that's not too confusing. But what you've done is you've created a new object with the gene variable containing the 81 things, if this is a 9x9 Sudoku board, and the fitness being evaluated by whatever fitness happens to be present in the UI. So you're adding those randoms to the next population. Then, probably the most complicated part, but still pretty easy, is the performing of the child generation process. So just keep in mind that we keep adding children until we fill the next population. So if I've added 100 of the 500 things that I need to add so far, then I'm just going to be adding 400, children using this process. So first, compute the sum of all the fitnesses in the population, and that is going to be this fitness sum. So why do I do that? Well, if I come back here to the roulette wheel selection algorithm, right? one of the things I need to do is calculate the total sum fitness of all the things in the population. I need to get this value of 200 here. So because I'm going to be selecting multiple parents, like 100 times probably, it would suck to have to iterate over the population each 100 times to get that value. So what I'm doing is we are going to compute that value once, and then in our roulette wheel selection algorithm, we are passing that value in as a parameter. That just prevents the roulette wheel selection algorithm from having to calculate that sum every time, right? So we calculate that fitness value, and then we have a while loop here. And we just say, while next population is smaller than settings.getPopulationSize, keep adding children by making new children. That's it. So how do we make the children? Well, first, we get a first parent by calling ReouletteWheelSelection. We get a second parent by calling ReouletteWheelSelection. Then we get a child. We're going to create 2 children for every 2 parents. Child 1, we are going to call crossover, and we're going to take the first half of parent 1 and the second half of parent 2 with the settings object, so in case we need those settings. Then child 2 is going to be the opposite. It's the first half of parent 1 and the second half, the first half of parent 2 and the second half of parent 1. I'll go look at those functions in a second. Then what we do is we take the first child and we mutate it, and then we take the second child and we mutate it. Now, I'm calling MutateIndividual here, which sounds like we're going to be mutating everything, but inside the mutation function, that's where we see if we're going to mutate the thing, okay? So that's where we calculate the probability and actually do it, whether or not we need to. Then we add those children to the population. But be careful, because every iteration here, we are adding 2 children, but let's say our previous population had an odd number of things in it. So we've already added elite stuff and we've added random stuff. So let's say we added an odd number of things by doing that. And if our population size is even, then adding 2 children every time will give us an off by 1 error in the population size. So make sure that you only add the second child if you still need that second child to fill the population. So if you need 500, you add the first child. Let's say you were at 499. You add the first child. Now you're at 500. Just check again before you add the second child to make sure you're not going to 501. And so keep in mind that the population, next population array should always be the same length as settings.populationSize. And yeah, right now, in order to make the blank template code that I give you work, I return the previous population. So your code, if you run it, you're just going to see flatness in the graph, because all it's doing is passing in the previous population and returning the previous population. So make sure you change that to next population for your code. All right, so now let's have a look at each of these functions that I said you have to do. The first one is roulette wheel selection. So you are passed in the population and the fitness sum. And all you have to do here is come over here, look at this pseudocode, and turn that into JavaScript. That should not be too difficult, okay? I really don't need to explain more than that. Let's go back here. The crossover is you're getting passed in 2 parents, and you're taking the first half of parent 1 and the second half of parent 2. Just keep in mind the only slightly remotely tricky thing here is if your gene has a odd length, then there is no even way to split it, right? So if you have 10 things, it's just 5 and 5. If you have 11 things, you just have to choose whether or not you take 6 from the first half or the second half, okay? And again, if you really want to, and you want to come up with a more clever way of mutating things that works well for Sudoku, feel free to put it in here, but I want comments when the behavior is not exactly what I wanted, okay? So anything that you're going to come up with is going to be more complex than this. So if you've done anything more complex, you'll get the full marks for this function. And so just be aware that what we're doing here is by default, we are taking the first half of a Sudoku board and combining that with the second half of another Sudoku board. So by the way we've done it, that kind of chooses it like right in the middle, and we're like splitting up this square. So if you think of some other way, maybe you want to do it by rows or by columns or whatever, just if you can fit it in there and it works and it makes your program better, I'm all for it. So that's the crossover part, and all you have to do is form this child gene that I've set up for you, and the fitness part is already done. So this line, don't change that line, because it's returning the object which has the gene and then the fitness of the gene already done for you. And then the last one, I believe, yep, is the MutateIndividual. So you get passed in an individual, which is that JavaScript array, and then based on the settings, you are going to either mutate that or not mutate that. So mutation changes a random index of the gene to settings.getRandomValue. So I'm going to be passed in a gene. If I think I should mutate it, I'm going to choose a random index, and then I am going to call getRandomGeneValue and set that to it. Now, if you come up with a better way of mutating for Sudoku, I'm all for it, okay? Just keep in mind that any changes and optimizations that you make also have to work for the other fitness functions, because we're going to be calling and making sure that you've solved all those convex problems, right? So if the thing you're doing here in the mutation completely breaks all of the other easy convex problems, then that's going to be an issue for your grades, okay? So just do the default if you just want the grades. You don't have to do this any better. So should you mutate or not? How do you choose that? Well, settings.mutationChance, what is that? Let me go over GA settings. Settings.mutation rate is 0.25. How do I know if I should mutate this based on 0.25? JavaScript has a built-in function which returns a random number between 0 and 1. If that random number between 0 and 1 is less than that number, that's all you have to check. Because a random number between 0 and 1 is going to be less than that number 25% of the time. It just happens to work out, okay? So that's what we're doing here. This function modifies the individual and does not return anything. So we are passing something into that. It is passed by reference because it's JavaScript, and it's not going to return anything, okay? It's just saying and the other thing that we have to do is that I've done this for you already, because this was a bug in previous versions of the assignment that someone spotted, is that if we modify the individual, we need to recalculate the fitness. Okay, so that's what that line does there. So don't change that last line. And that's pretty much it for the assignment. That's all the files that we have to worry about. So let's quickly go into the marks. We've got our standard 5% here. Oh yeah, so I want you to be able to solve a 2x2 Sudoku pretty easily. So if I refresh this and change this down to 2, if your program is taking 20 seconds to solve a 2x2 Sudoku, you've got something wrong with your program. That's a pretty easy thing to solve. So this is a solved 2x2 Sudoku. And if you can't solve a 1x1, I don't know what to tell you. All right, it makes progress towards a 3x3 Sudoku. So just come back and watch the video, and if you're sort of getting the same, graph, same sort of thing, okay, things are becoming white. If we leave it for a minute, most of the things are white. That's what I'm looking for. I do not expect you to solve the Sudoku. It is not a requirement. The GA solves all of the non-Sudoku fitnesses for 9x9. I mean, it probably should solve it for all the other ones as well. Like if I crank this up and change this to some values, the only thing that really changes is that we have to run it longer so that we eventually mutate things enough to hit those random values. But it still should, you should see this line go up, right? That's what I'm looking for here. Back in the code, graph of fitness over time makes intuitive sense. Like if we look at that and it's like the randomness is going up and down and like that's a bit weird. Individual functions, I've just assigned arbitrary marks based on how much work I think each function is to make the marker marking easier for them. But keep in mind, even though, for example, you have roulette wheel selection, 15%. That doesn't mean that you can do everything but roulette wheel selection and get an 85, because everything else will break if you don't do roulette wheel selection. right? So these things are like, yes, I'm marking that part out of 15, but if that part doesn't work, then this stuff certainly isn't going to work either, right? Also, if you leave out mutation, if you got, you're 10 minutes before it's due and you leave out mutation, it's very likely that your program won't be able to solve anything without that mutation. Okay, so just keep that in mind. And for the 6980 version, there's this part at the end where you must have one theoretical enhancement implemented to this. Now, I know I'm going to get 25 emails. Is this enhancement good enough? Is this enhancement good enough? Okay, let me give you an idea. This is like a fallback idea, but here's something interesting. Let's have a look at 3x3 Sudoku, and let's look at the graph over time. Let's run it for a little bit. After a few seconds, we're going to find that it gets stuck, right? Not yet. Okay, starting to get stuck. So, if you're stuck, what is one way that you could possibly get unstuck? Yep. Maybe put a bunch more randomness in there, right? So if I get stuck, if I've detected somehow that for some number of generations I've gotten stuck, maybe I put in a bunch of randomness. And then after a little while, I turn that back. Let's see, did that help me? Didn't happen to help me there. Maybe I turn off elite genes for a second and then I go back, right? Now that may have undone a bunch of progress, but if I'm truly stuck, maybe this will help me get back there and actually, get out of this local minima. So let me see, did it? What is this? What is this value? Oh, when it gets so small, I can't mouse over it anymore. But yeah, that's actually higher. So that actually did help me. So one of the things you can do is go out there and research ways that people running actual genetic algorithms for their research or their, industry application or whatever, do things like detect that I am getting stuck and modify settings or parameters to see if this will help me get unstuck. Okay? So, now, you can't just do that one thing of if I haven't changed in 100 generations, put the randomness up for a bit and then put it back. It's got to be a little bit more complex than that. But hopefully you see what I'm getting at here. There are all sorts of different ways that you can do recombination, for example, that may be more clever. So for example, if you wanted to take two parents and recombine maybe in a checkerboard pattern or take these, whatever enhancement that you make, one way that you can do that is to come down here in your code and say, okay, if using improvement, crossover enhanced, otherwise not enhanced, okay? What I'm going to try to do, because I just thought of this, I'm going to actually, before I release this, so this will be there when you wake up tomorrow, I'm going to move this use improvement to the settings and put something in the UI to be able to turn it on or off. Okay, so you can modify in real time this setting, and that'll just be way easier for the marker rather than have to modify the code and then go back. So this use improvement will be in the settings, and I'll just have GASettings.useImprovement. So if you want to read that, that'll be settings.useImprovement. So down here, if settings.useImprovement, crossover improved version or whatever you've written. And like always, feel free to add whatever code you want to this file. Just don't rename any of the variables or functions that are already there. Cool. I think in terms of programming, assignment 5 might be less lines of code, but I think in terms of easiness, this is probably the easiest conceptually. Graph go up, you're probably good to go, right?